Thank you for the kind introduction. So my name is Neelkamal Mallick. I am from Indian Institute of Technology, Indore. And today I have this privilege to talk about the topic where I am working for quite time now, application of machine learning tools in heavy ion collisions at the Large Hadron Collider. As the topic suggests, it's a very broad direction, but I will specifically talk about my analysis where I'm involved in. This is my outline. I will talk about the heavy ion collisions and why they are important. And then I will go to the estimation of impact parameter and transverse velocity observables. And I will talk about the deep neural networks that we use to develop a model to estimate the elliptic flow. And at the end, I will conclude my talk with summary and outlook. So we all know that the matter is not continuous, but discontinuous because it has atoms inside. And the atoms are again subdivided into electrons and the nucleus. And the nucleus consists of proton and neutrons. In 1964, Professor Gell-Mann and George Wake postulated independently that these protons and neutrons, those are called as the hadrons, they have further substructures known as the quark. And it was experimentally observed that in 1968 by the SLAC US team that yes, proton and neutrons does have substructures known as quarks, and these quarks are the fundamental bits of matter that we are aware of, and the gluons are the carriers of strong force. And the theory of strong force is given by the quantum chromodynamics, where we discuss about the quarks and gluons and so forth, so forth. And there is a phenomenon known as the quark color confinement, where we talk about that free quarks and gluons cannot exist under a regular temperature or pressure. That means that you cannot find a free quark or a gluon ball just lying around. But what they do is that they clump up together and to build mesons, which are the two quark structures, and baryons, which are the three quark structures. So basically, quarks and gluons are confined inside hadrons. And here you can see this is a typical meson structure, where this is example for pion, where you have one off quark and one anti-down quark. So mesons are two quark structures, and this is the proton, where you have two off quarks and one down quark. And what are the heavy ions? The heavy ions are the nuclei of lead, gold, or xenon nuclei. Because they are heavy elements, we just strap out the electron, and what is left is the nucleus, which is positively charged. So that is called the heavy ions. Okay. So what we do is that we have built the powerful particle accelerators. This is the aerial view of Large Hadron Collider present at CERN, Switzerland. And here we have four major experiments going on. One is ALICE, ATLAS, LHCb, and CMS. These are dedicated detectors for specific physics analysis. And if you look around, this is a very long tunnel built under about 100 meters underground, and the circumference is about 27 kilometers. And what you have inside is these tubes, which are superconducting electromagnets. Operating under cryogenic, they are cryogenically cooled, so they can deliver maximum electrical and magnetic energy to accelerate and deflect the charged particles. And by doing so, we are capable of achieving for proton-proton collisions the maximum root S energy, or you can say center of mass energy, is about 13 TeV. So that is used. And it has the technical, it has many technical marvels, but theoretically, if you speak, when you accelerate particles, maybe as small as protons, but when you accelerate it to ultra relativistic speeds, it acquires mass. So at every stage, you have to accelerate it phase by phase. So there are many small accelerators built inside before moving to the final Large Hadron Collider. Okay, and this is the ALICE detector, and what these detectors do is that they are like cameras that tries to capture the events. So by event, what I mean is that when you collide particles, they produce a lot of other particles. We know that energy can be converted into mass, and so we can create particles from the energy. So this is the typical picture of an event record from ALICE detector. you can see that two lead nuclei, when they collide together, they give rise to a lot of particles, and the particles move towards the detectors with the curved path, because obviously they have charge and they interact with the magnetic field, and they produce these beautiful tracks. And you can see that the number of particles being produced in a single collision is huge. It is about 2,500 particles in the top central collisions. Okay, so what happens in such collisions is that we have the lead nuclei, and these nuclei, when we accelerate it with ultra-relativistic speeds, they are Lorentz contracted. And when they are Lorentz contracted, their particle density and energy density increases. And at the collision point, the energy deposition is pretty high. It is about 0.5 GeV for Fermi cube. And under this much energy, the contents inside this nuclei are the protons and neutrons. And if you further go inside the quarks and gluons, under this temperature, they start to melt down, and they form a thermally equilibrated state of hot and dense matter known as the quark-gluon plasma. And this quark-gluon plasma is formed in the shape of a fireball, and this fireball then starts to expand and further cool down through radiation and direct photon emission. And during this process, these quarks and gluons, which are commonly known as partons, they try to inelastically collide among themselves, and they undergo the process known as hadronization, where they combine together and then they form hadrons, which are the again back to the hadrons. And these hadrons then collide among themselves elastically, and further they move towards the detectors, where we find their tracks, and we observe their momentums through the detector. Okay. We study heavy ion collisions because we want to produce and observe such a state of matter. And this quark-gluon plasma is believed to be formed just after a few microseconds of the Big Bang. So we can say that heavy ion collisions recreate Big Bang kind of scenario in a miniature level inside the labs. Okay. So there is one important parameter known as the impact parameter, which is given by the definition is like this, that the transverse distance within the center of the colliding nuclei. So if you take the z direction to be the beam direction, and the transverse plane will be the xy, so these are the two colliding nuclei. And you can see that the nuclear overlap region is depending upon the distance between the two centers. This is given by the impact parameter. And obviously, if you have the complete head-on collision, then the nuclear overlap region will be more. And if you have slightly deviated, that means the impact parameter is more, then you will have a small region of overlap. And that will definitely affect the final state particle production. And why the impact parameter is important? Because it is of the order of a few Fermi, and it is impossible to measure from experiments. But we can infer the value of impact parameter from the multiplicity distribution. By multiplicity distribution, I mean the number of particles that we observe at the end of the collision. So here, if it is a central collision, head-on collision, then the number of particles will be more. And if it is a peripheral collision, then the number of particles will be less. But there is no exact way in which we can measure the impact parameter directly. And there is another observable which is quite new in heavy ion collisions. So this is the transverse velocity, and what it does is that, okay, so if you observe this diagram over here, for every collision, there are two possibilities. If the particles will move back to back, producing a jet, then that will be shown like this in a red cone. Or they can produce symmetrically in possible all directions. There are two possibilities. So this structure over here is a jet, and the blue one is given by the isotropic events. So this transverse velocity is an event-safe observable, which can calculate the exact value of whether the event is towards a jetty event or isotropic event. So for jetty events, the velocity value is close to 0. And for isotropic events, the velocity value is close to 1. And this can be calculated over this expression. But obviously, if there are the number of tracks is more, and the summation is taken over the tracks, so it takes a lot of iterations to find the velocity value for one single event. And here the complexity is finding this n vector, which is known as the velocity axis, It will be different for different events, as this term inside the bracket should be minimum given the this unit vector. This is the scenario. So for the time being, we have the transverse velocity calculated for PP collisions. But for heavy ion collisions, as the statistics is more and more number of particles are produced, we thought that we can have a machine learning model where we can train the model with simulation, and we can predict the transverse velocity value with some final state observables. I'm not going into the formula directly. And we also think about the estimation of impact parameter from some final state observables where we can actually get a number for the impact parameter. So this motivates us to go further. And we have, okay. So here we have some final state observables which we can directly get from the detectors. So we have the multiplicity, d in charge over d eta, and we have the multiplicity in the transverse plane, and we of course we have the mean transverse momentum. So these input variables, so when we calculate the Pearson's coefficient with the impact parameter here and the transverse velocity here, we observe that they are quite nicely correlated, as you can see. And the impact parameter is inversely correlated to multiplicity. That means for head-on collisions where the impact parameter is less, we have more number of particles. So with this correlation, we see that, okay, these parameters are good enough to train a model and to calculate the impact parameter and transverse velocity. And we build a model based on the gradient boosting decision tree. And where, okay, so where we have, these are some tuning parameters. We have used the loss function to be the least square loss. The learning rate is 0.1, number of trees is 100, and the training sample size is 60,000 events. So 60,000 events corresponds to like around 20 GB of data if you take heavy ion collisions. And then we calculate the system size dependence. So when we increase the number of events, we see that the training accuracy is increased. And at a certain point, we see that the training accuracy saturates. So at this point, we stop and we take that, okay, the 60,000 events are enough to train the model. And you can see the comparisons for the different loss functions over here. We have least absolute deviation, least squares, and the Hubble loss. And we see that fairly all of the three loss functions perform nicely. Finally, we see in the spherosity class, we see that the least squares actually performs better. And here the difference between these methods at the 100th iteration can be taken as the systematic uncertainty for finding these estimations through GBDT model. Okay, so here are the results. If you plot the true value versus the predicted value, you can see that all the points are fairly lying on a straight line inclined at angle 45 degree. That means most of the points are accurately predicted, and some of the outliers are also present. And for spherosity also, we see that the same structure appears because some of the points are on the middle and a little bit of outliers are there. And the impact parameter domain is from 0 to 20 for me, and the spherosity is of course 0 to 1. So 0 is the jetty kind of events and 1 is the isotropic events. And okay, so and for heavy ion collisions, the spherosity distribution shifts towards isotropic. That means the probability of an event to be isotropic is more than compared to the jetty domain. And here we have the comparison between prediction and true values of impact parameter. And in the bottom plot, you can see that the ratio appears to be completely flat, and it says that overall, this is the 1-1 correlation, but overall, when we find larger statistics, we see that the accuracy is close enough. And here also. And here we find some discrepancies because the jetty events are less in statistics. So the model is a bit biased towards the isotropic events, and it performs better in this domain, but it is slightly deviating in the jetty domain. Okay, so then we try to apply it to the different centrality classes. So initially we had this distribution is for minimum bias distribution. That means we do not consider about the centrality of the collision. But here, when we apply it to different centrality classes, we see that for 0 to 10%, 40 to 50%, and 60 to 70% centrality classes, we see that the distributions are like this, and it starts to shift towards the JT kind when we move towards the peripheral collisions. But for the most central collisions, it is always aligned towards the isotropic kind. So the conclusion is the machine learning model actually preserves the centrality dependence of the sphericity. Okay, the next part of my talk will be the estimation of elliptic flow. Okay, so if you look into this figure, these are the two incoming nuclei, and at the collision point, this is the nuclear overlap region. So the nuclear overlap region is not symmetric. There is initial spatial anisotropy in the collision geometry itself. And if you just take this geometry to the 2D plane of XY, you see that this perfect ellipsoid, and here along X direction and Y direction, there is a finite pressure gradient. And due to this pressure gradient in the QGP medium, particles which are coming in the X direction will have more momentum as compared to particles which are coming along the Y direction. And thus the spatial anisotropy due to the initial geometry gets converted into azimuthal momentum space anisotropy, where we detect the particles in the final state. So this refers to the elliptic flow, and it is defined as the azimuthal momentum space anisotropy in non-central heavy ion collisions. And it is defined as the okay, if you expand this term dn by d5, which is the number of particles in the azimuthal angle for azimuthal angle. So if you expand this term in terms of this Fourier series 1 over 2 pi and this bracketed from inside, then you have this then you can have these coefficients of Vn, which are the different order of harmonic coefficients. And if you take n is equal to 2, then that corresponds to this elliptic flow, which can be calculated by taking the average of this thing, and where phi is the azimuthal angle. Okay. So now we want to implement the deep neural network to understand the flow dynamics from final state particle production and to predict the elliptic flow. So we have this deep neural network. Like the deep neural network has the neurons like present in animal brains. So this has 3 key layers. One is the input layer, where all the features are fed into the machine. There are hidden layers. And finally, we have the output layer. So in this case, as we are doing a regression, the output layer has only one node. And these neurons actually talk to each other through different weights. And there is activation function that normalizes the values that the weights can take. And we have the cost function. The cost function is the error, estimates the error between the true value and the model prediction. And the optimizer is the algorithm that minimizes the cost function to get the better result. And by minimizing the cost function, it updates the weights associated with these neurons. So this is more or less about the deep neural network. Now we use this deep neural network to estimate the elliptic flow. So if you can look into this picture over here, this is the eta phi space for the lead-lead collision at 2.76 TeV. Here you can see that there is a jet there is a jet event, and you can see that one jet is coming here, giving more energy. This is a transverse energy, but another jet is a bit dominated. So this artifact is this is actually related to the medium formation, because when you have medium formation, one part of the jet actually comes out, but the other part goes inside the medium and it loses its energy. So this is the typical picture of the eta phi space. So what we did is that to predict elliptic flow, which is actually an event property, that means for each event you have one value of elliptic flow, we have the different track properties. So we took the eta phi space as the preliminary input space, and we applied different layers like PT, mass, and this log center of mass divided by some constant to be the 3 layers in the eta phi space. And we have this the beautiful 2D plot. So where this is actually one event in the lead-lead collision 5 TeV from AMPT simulation. It has 32 by 32 pixels, and you can see that these different weights, PT, mass, and this log root SN by S0 changes the plot slightly, and these informations can be taken as the input to the neural network to learn and predict the elliptic flow. So in our DNN model, we have 32 into 32 pixels for each layer, and we have 3 such layers. So that makes 3072 pixels for each event. And we have this input layer 128 nodes. Then we have 3 dense layers, each of having 256 nodes, and the final layer has only one node, which is the V2 value itself. And we have taken the ReLU activation function, which looks like this if you plot it. For the first 3 layers, and the linear activation function for the final layer. And the training sample has 10 to the 5 events, closely 25 GB, and the validation set has 10 to the 4 events. So these are the results of when during the training, you can see that the model is not overfitting or underfitting, because you can see that there is a minimal difference between the validation set and the training set. And also, if you plot the true to the predicted values, you see that all the points line up nicely along this 45-degree angle straight line. And there are, of course, a few outliers present. And the mean absolute error is 0.006. And when you plot this V2 as a function of centrality, we have 3 sets of points here. The black points are the Alice data points, which are calculated by the detector taking real data from the experiments. And this AMPT is the simulation model where we are taking the data. And this DNN is the prediction from the neural network. And here you have the ratio to AMPT and data, and you have this DNN to AMPT. So you can see that the neural network follows the simulation training. And the AMPT to data, of course, this is an event generator, so it will have its limitations. So at some points, it's going above and below. And when we apply this is the training done at 5 TeV data. So when we apply the training of 5 TeV data to a lower energy, say 2.76 TeV, we see that it actually preserves, the DNA preserves the energy dependence of V2, and it accurately predicts the simulation values. Okay, so this is the first set of results. And the second set of results would be when we apply it to different PT beams. So we have here the 3 figures corresponding to 0 to 10% centrality, 40 to 50%, and 60 to 70%, V2 as a function of PT. So the training is done in the wide range of 0.2 to 5 GeV. And then we apply different cuts in the PT beams. These are the PT beams. And we find the value of V2 for each PT beam. We can see that in the lower PT domain of 2 GeV, the predictions are pretty nice. But as we move towards a bit higher PT, it starts to deviate a little bit from the simulation. So we can say that DNN preserves the PT dependence of V2, but there is a slight mismatch between the points at the higher PT value. So this is the work so far, and I can conclude that the implementation of machine learning tools is quite successful in predicting the impact parameter, transitorosity, and elliptic flow. And the model actually learns the energy dependence, centrality dependence, and PT dependence of particle production, as we see the good agreement between the simulation and prediction. And the good part is you can take final state particle parameters, and you can estimate this initial parameters like elliptic flow, impact parameter quite efficiently, and the application is obviously faster once you have the model built. The next part of the work will be to estimate the non-flow contributions and how to reduce it, and also the estimation of identified particle elliptic flow. And we look forward to work in the quark and gluon jets also. So this is all about my talk. Thank you.
Thank you very much, Neelkamal. Questions? Please. The speaker.
Yes, during the training, we have this wide range from 0.2 to 5 because we want to train the model with all possible information that we can give. But when we apply it to different PT beams, so this is the output. So obviously the low PT domain will have higher statistics. So the model is a little bit biased towards the higher statistics because it replicates what it sees. So this is the good agreement. But when you move towards the higher PT, so obviously the statistics are a bit less, so it starts to deviate a little bit. But I think this can be further fine tuned with a bit more data. And currently we are running with these many events. So it takes a lot of time to generate these events. So in future, we think that we can overcome this problem.
The number of events is for the whole PT range.
Yes, yes. This minimum bias events. Yes, yes. Thanks.
Other questions? There is no, we have to move on, and thank you very much.
Thank you.
Neelkamal.